like to talk about adaptive filters. In particular, I like to talk about adaptive filters with vector level outputs. So in this case, we're talking about having an input vector x and an output vector y of desired signals. So you may have seen these as a single input or a single output with maybe a whole vector inputs. But you can certainly make this work if I have a vector of outputs, which means I'm going to have a vector of desired signals. And if you look at the vectorized form, this becomes kind of the framework of which many other neural network layers get built up from here. So you have an error vector coming in, an error vector from the target and the actual signals. There's a vector matrix multiplication between y and x, of which that's going to be a matrix W. And then matrix W is going to be adapted by an outer product of minus 2e to the x transpose. And this, of course, comes from a error surface optimization, which is why you get a minus 2. You get a 2, well, you get the minus 2 because then you're moving against the gradient in that optimization. Okay, so when you do that, I can then say, well, what is E? And I kind of already know that because I know that E is this difference. I also know that Y is then W and X, and that gives me a whole range of things of which I can do. Okay, now building into sort of key assumptions, which again can never really be said too many times, but is to say that the vector of x is zero mean, that x is moving at a fast time scale, and the weight adaptation is at a slow time scale. These are separated time scales. This is essential for the dynamics to get the adaptation to work. And these have some very important properties, one of which being because it's zero mean, the integral goes to 0, the expected value goes to 0. The other aspect of the weights is that because it's moving slowly, the expected value is roughly that term. Then you take this equation, it then drops into two terms, one of which is Q, which is the covariance matrix. And that's, again, going to consume to be relatively constant in terms of its over the integral dynamics that I get over that slower time scale, the differential equation, and a similar one here for R. What's nice is once I've created this differential equation, I know what the steady state is. It's W equals RQ inverse. And then if I want to get further into the dynamics, further in terms of what the solution looks like, I'd realize, well, Q, and just starting with this differential equation, which beautifully does solve this whole problem for me, this Q is going to then be E lambda E transpose. Because it's a symmetric matrix, I can decompose that where E is a set of ordered eigenvectors, lambda is the ordered eigenvalues. And it turns out that I know that all the eigenvalues will be greater than or equal to 0. So that also gives me some clues as one further analyzes this. And what's nice is that I can then plug this in and it's going to be W A E transpose. So I'm projecting W along the eigenvalue basis and seeing what remains. And I'm going to build from there. And what's interesting is I can take that structure and evolve through, and I get E transposes come through, this E transpose goes away. Eventually I get E transpose on both sides, multiply by E, and I notice that I got an A, I've got an 8, and the main matrix here is diagonal. It's always going to be positive or 0. For the most part, those are always going to be positive eigenvalues, unless like there's some signals that didn't exist or there's a degeneracy. And then I will have sort of the resulting solution, which includes the eigenvalue part of the basis. And now this allows me to ask questions about how does this converge and what speeds does it converge, depending on, for example, the eigenvalue spread and how I might look at the overall analysis of this problem. But this becomes essential not just in terms of how does an adaptive filter work, it's also essential in terms of getting a sense of how most sort of other nonlinear structures, most non-neural networks and other things will operate.